too. And if you're interested in volunteering, that's another thing too. But anyway, that's enough of that spiel. Let's get into the good stuff, shall we? Let's go to the rocks. I'm going to share my screen and off we go. All right. Give me a thumbs up if you can see a Minnesota North Shore geology screen. All right, good, good, good. So yeah, that's the topic of conversation this evening. And I love talking geology. I will say that I am not a professional geologist by training. I am a naturalist who loves geology and has learned a ton in my career. And boy, you know, if I had it to do it over again, I might have majored in geology, but I didn't. I was a biology major. So yeah, I am delighted to get started with stuff, but we are going to concentrate. I could talk a lot about lots of different kinds of things. Minnesota has fascinating rocks. And we could get going on all kinds of rocks and stories and stones and all over Minnesota, but we're going to concentrate on the North Shore this evening. And that really all starts at the North Shore. Stuff begins roughly 1.1 billion years ago with the beginning of what we call the mid-continental rift. And yeah, what's a mid-continental rift? Well, you've probably heard about rifts in other places of the world. The African rift is world famous, but we had one here in the Midwest at 1.1 million years ago. Now, honestly, were we really the Midwest 1.1 million years or billion years ago? No, we weren't even Pangea yet, quite honestly. This is a long time ago. We weren't even really fully North America at that point in time. So there's a lot of stuff going on geologically speaking at that point in the development of the different continents and the earth. But we think what happened here that created the rift, and this is literally the earth splitting apart and molten lava from within the mantle of the earth flowing to the surface. And we started the process of about of what was later to become Lake Superior about 1.1 billion years ago. And the illustration at the bottom kind of shows that molten lava got close enough to the surface to open up a hot spot. And that's what we think started the whole process. And basically lava flows happened over the next 15 million years or so, plus or minus a couple million years. We'll talk more about that whole idea as we go along, but there were literally hundreds of flows. And so this is molten lava, but you kind of have to understand that this was flood basalt and floodplain basalt. John Green likens it to, okay, you got a flat bottom boat and the boat is cruising along on the lake and all of a sudden it develops a split down the center. How's it going to leak? Well, it's going to bubble up through that leak and it's going to spread out across the floor of the boat until until you're not a boat anymore. And that's a problem. But in the case of the basaltic lava flows, they were pretty, this is not volcanoes erupting all over the place, although we might have had some of that. And we'll talk a little bit more about that as we go along. But these flood basalts continued for 15 million years or so. It's estimated that there were so many flows that at places on the North Shore, the crust is as thick as almost 19 miles thick with all of these lava flows. In fact, there are places, when you get down closer to Gooseberry, there's a spot down there where they estimate that it might be as much as 35 miles thick. That's a lot of stuff. And just to put that in perspective, folks, the crust of the earth, which is, what we're accustomed to moving and grooving on, is typically somewhere from 3 to 10 miles thick. At 19 miles thick, we're significantly thicker than that. And at 35, yeah, we don't even, it's just crazy thick. And that's part of the Canadian Shield, or the craton for North America. And the craton is the center part of a continent, kind of where a continent developed from, or the oldest portion of the continent, and things happen spreading out from there. So yes, we're part of the North American craton. We call it the Canadian Shield, and it's all very old rock. In this case, the 1.1 billion year old rock is pretty old. It's not the oldest rocks in Minnesota, but it's pretty old. It's part of what we call the Precambrian era. And so, yeah, lots and lots of lava flows. A lot of people say that lava doesn't have layers, but I challenge you to look at that picture on the left-hand side and tell me that lava flows don't have layers. Well, we'll get into that some more as we go. The rift, the mid-continental rift, which really kind of split down what we would kind of consider the center of Lake Superior. As the rift kept going, it kept getting deeper and deeper and deeper as lava continued to flow out. And imagine this, okay, the crack where it's all coming out is in the center. That's going to be where the lava's the thickest, correct? And then as you go out from that, as it spreads out, it gets thinner. And what eventually happened is that all that weight in the center tilted everything and formed what we call the Sawtooth Mountains on the North Shore. They're not mountains that form in the traditional way. We know that the traditional way for mountains to form is either continental plates slamming into each other, or a oceanic plate subducting underneath a continental plate and causing mountains to form that way. This is not that. So yeah, the fancy and kind of double entendre type word in geology is called orogeny. This is not that. This is gravity going thunk. And that's what forms the Sawtooth Mountains. And if you look at that picture on the right-hand side, you can kind of see that angle stays about the same. It varies a little bit from 15 to 25 degrees or so up and down the North Shore. Yeah, and so we're talking about molten lava. And that means that all of the rocks that we're talking about are igneous rocks, or things, molten rock that comes from rock within this, the center of the earth. And in the igneous rock world, we create what we call the igneous rock square. Some lava bubbles out on the surface and cools very quickly. Other lava cools slowly underground. And so when you're looking at this designation, and we're going to concentrate on four main types of rocks. We're going to concentrate on rhyolite, basalt, gabbro, and granite. And you'll notice that this drawing, it goes from lighter to darker. And we'll talk a little bit more about what that differentiation means. And then these guys are on the top this way, and these guys are on the bottom on this side. So the stuff that's on the top is the stuff that cools quickly on the surface. The stuff that's on the bottom is the stuff that cools slowly underground. Basalt and gabbro, mineral-wise, are the exact same thing. Basalt cools quickly on the surface, and gabbro cools slowly underground. Same thing over here. Rhyolite cools quickly on the surface, granite cools slowly underground. And therefore, these guys you're going to expect bigger crystals. These guys, you're probably not going to see individual crystals much at all. So let's take a look. What was the difference? Why did we go from light to dark? Well, that has everything to do with the main components that are in the lava. Silica is the most common mineral on Earth. And you can see in both of these types, by the way, the top here is the dark side of that chart. This is going to be the basalt and gabbro, or if you want to play professional geologist, you're going to call it mafic lava, which means it's iron rich. If you look at the iron content for this stuff, it's up at 14%. Silica's at 48%. Now let's look down here at the lighter colored stuff. That's going to be rhyolite and granite, and that's going to be felsic. Look at this, much higher silicon content, 68% versus 48 up here, and iron content's down to 5 here versus 14. So the iron-rich side of the spectrum is one type of lava and lava flows, and the higher silica content makes others. So let's just explore that a little bit. So yeah, if you go to a beach on the North Shore, here's some of the usual culprits. So take a look at those guys. Take a second for yourself and kind of group those together, how you think they might belong. And then we're going to sort those out according to the igneous rock square in just a second here. So I'll give you about 20 seconds here. Take a look at that. Who's related to who? Who looks like who and why? All right. You don't have to answer the question, just mentally do it in your head. So we'll give you a little peace and quiet for a bit. And let's go ahead and let's divide those guys out. And I sort of did it for you here on this page. Here's our igneous rock square. The basalt guys are going to be these up in the corner here. Now, those 3 different pictures don't look anything alike, do they? We've got a couple of different forms of basalt going there. This guy down here is our gabbro, so that one goes with this. This is a granite. This is a kind of green colored granite that we have in Minnesota. And then this is rhyolite. So these are breaking it up. Now, if you look at this one, this is kind of your basic basalt. Basalt is often, but not always, on the North Shore, kind of a black colored rock. But I'll warn you, it can also be brown and it can also be red. Whoa. That makes it sometimes problematic to tell what's going on, but often you can look at the other crystals that come in later, some of the stuff that fills in the gaps and the holes. I should have put one more rock picture in here, but I didn't happen to have one to stick in there. When you think about basalt and its different forms on the North Shore, sometimes you'll see it like this, that looks really speckly. Some people call it snowflake basalt. This is a particular form, and it's real common on the North Shore. This is called ophitic basalt. And ophitic basalt just means that we have these little round nodules of pyroxene, which is a mineral that tends to make these little guys. And the interesting thing about this rock is that when it weathers in these little round marbles. So have you ever had the experience of cruising along on a trail on the North Shore, maybe on the Superior Hiking Trail, buzzing along, and all of a sudden it's like there's all these little BBs on the trail and you're working to keep your balance? Well, that's ophitic basalt weathering, and those little round nodules are what are those little pyroxene nodules disattaching from the rest of them. So yeah, pretty cool. That's ophitic basalt, but it's still basalt. this one down here in the lower left-hand corner of this upper right-hand corner, too many corners there. We've got another piece of basalt. Notice that the background color is more towards the brown side of the spectrum, but this one's interesting because it's got a bunch of little rectangular crystals in it. This is called porphyritic basalt, or that's called porphyry. And what happens with porphyry? Well, think about molten lava beneath the surface of the earth. It's getting there. It's ready to erupt out or flow out onto the surface. But for whatever reason, it's not getting right to the surface right away. It's actually hanging just below the surface. And what's happening is the minerals that crystallize out at the highest temperature are starting to crystallize. It's kind of like making fudge. You know how you start out with all that chocolate and it's nothing but runny chocolate, but eventually it starts to lump up, or your oatmeal in the morning. That's the other thing that I'll use for that. And it eventually solidifies to the solid mass that you want to eat. But the porphyry is the mineral that crystallizes at the highest temperature. And that crystal has that characteristic rectangular shape. That is a feldspar. And that's why it does that. So yeah, this is porphyry. And the other guy up here in the upper right corner is pretty much your plain Jane basalt. Notice that you can't really see individual crystals. It looks like a solid color and it's one entire mass. You can't really see anything differentiating that. Now, the one that I left out that I could have added to this corner is vesicular basalt. And that's the one that's got all the bubbles in it. And we'll talk about how air bubbles get in basalt here in a little bit. But those air bubbles can either stay empty. If they stay empty, it becomes vesicular basalt, or basalt with bubbles. And if those bubbles fill in with crystals eventually, and filling those slots up with crystals, it becomes amygdaloids, and that becomes amygdaloidal basalt. So there's all kinds of versions of basalt. And the truth of the matter is you can have all of those same versions over here when you're talking about rhyolite. Fast, cool on the surface, but there's often other things going on with that fast, cool, like lots of air bubbles or things like that in different layers of the lava. And we'll talk more about that here in a bit. Down here, you've got gabbro, that's the relative of basalt, but this cools slowly underground, and it has lots of different size crystals in here, and you can actually physically see those crystals within the whole rock. And over here, we've got granite that also has multiple colors. You can see pink in there, you can see green, a little bit of white. If you look really closely and you're not looking long distance through a computer screen, you might actually see some black crystals as well of different kinds of minerals. And what's happening in these slow cool rocks is different kinds of mineral are getting a chance to group together, which is why you can see all those different colors. Up here, those minerals are all still there. They're all the same guys that are down here. It's just that they're not getting the time to form those crystals. So here's our basalt, gabbro on the mafic side of the spectrum, or the iron-rich side, or the dark side. That darkness tends to come from that iron. That iron is what gives it that dark color. On the other side, we've got lighter colored in general, often with a red coloration here in northern Minnesota. If you look at rhyolite in other places in the world, it'll often be white. But here in northern Minnesota, it's red. And this too it forms at a lower temperature than this. This is the really, really, really super hot stuff. But you don't want to be dipping your toe in this stuff either. It's still plenty warm when it's happening, but it's a cooler temperature. And then granite. Now I did throw a couple of other rocks in there that you will see on the North Shore. Granite can metamorphose, and the northeastern side of Lake Superior from from Canada will get a lot of this kind of stuff. Granite that's been pushed and shoved and heated up highly and gets these stripes in it. You can still see the colors of granite. In this case, it's a black and white type granite, which we see frequently, but it has metamorphosed into another type of rock called gneiss. And I don't know why I didn't put that in there, Gneiss. So yeah, here's where I start telling bad geology jokes. Are you ready? Okay, here we go. So granite, if you push it through heat and pressure and change it, it becomes nice. And what you say is, I'm a nice person. Don't take me for granted. Yeah, I know. They're the only jokes I remember, only the geology ones. I can't do the others. This one down here, this is also really common stuff that you'll see on the shore. And this picture really doesn't do it justice. These guys are shiny. They're really shiny, and they are called chert. And most of them are coming thanks to the glacier having shoved it from other regions around the lake, particularly up the Gunflint Trail. So chert is shiny, and it's got a really high quartz content, and it forms from sedimentary. Sedimentary means rock piles up. In this case, with the chert, it's often nodules that form underneath water, and a good portion of Minnesota spent a lot of time underwater. And the glaciers bring that down to the beaches along the shore as well. So there's kind of the basics of what we see. Now, how does it affect lava flows and what's going on? If you have silica-rich lava, you're going to have really explosive eruptions. So here's some examples of volcanoes that are continental rock that is loaded with silica. And Mount Pinatubo in the Philippines is a continental high silica content volcano. So is Arenal in Costa Rica. And Mount St. Helens, when it blew in 1980, blew off half the side of one side of the mountain. Heavy duty silica content. Again, silica being that most common continental crust mineral, and it's lighter than the iron, and it floats like marshmallows at the top. Whereas the iron-rich stuff more frequently is in the oceanic plates and down below and sinks because of that iron content. But yeah, iron-rich lava flow is a much more mellow event. Here's a guy cruising along next to molten lava, probably in Hawaii, and he's not dying, he's not burning to death, or he'd be running the other way in a hurry. But because I'm sure it's plenty warm there, but as long as he doesn't try and stick his toe in the molten lava, he's going to be fine. And here's a fissure eruption in Kilauea, Hawaii, and that's kind of that, what I was trying to describe earlier, that flood basalt formation that happens. So yeah, if you look down the North Shore, and we'll do that a little bit more later, but you see mostly basalt because it's coming from the mantle. The mantle is melting and kind of getting a pipeline up to the surface, and most of that is going to be pretty mellow, not much eruptive. There'll be some splash with it, but this molten lava is going to intersect with the crust, and it's hot enough to cause some of the crust on the bottom side to melt, and that'll form rhyolite. And that'll be a more explosive form. And we do have some rhyolite on the North Shore, but most of it's basalt. Here's a map to kind of give you perspective on that. Basalt is the green color here. Pink is the rhyolite. And then we've got yellow, that's the gabbro. And by the way, folks, this gabbro is part of what we call the Duluth complex. And it's the second largest complex of gabbro that we know about on the earth. Anybody know where the first, the biggest one is? Well, that's in South Africa. But here in this area, we've got the Duluth complex, which is the second largest one that we know about in the world. And then a little bit of granite in these little orange blobs in between. That's all the cooled slowly underground stuff, whereas most of the surface stuff is closer to the shore of the lake. So how are we doing? Have I spouted enough geological terminology? If not, we'll work on adding some more to the list. I throw this slide in because this one shows a little bit more information, and it indicates these little orange blobs, which are where we know we have copper and nickel deposits. Take a note of where those are. This is part of the mid-continental rift rock, and everything outside of that is older. So this stuff up in here, this is 1.1 billion year old stuff. This stuff out here, 2.7, 2.5, that neck of the woods, it's much older. But it's this interface between the mid-continental rock and interfacing with this older rock that results in these copper nickel deposits. And yeah, we all know that that's a pretty heavy duty controversial thing. And as citizenry, we've got kind of a job to figure out what's happening with that. I'm not going to say a whole lot more about that at this point, but it's definitely a cause for conversation. And I think as citizens, we have a duty to try and figure out what the best answer is to all of that. So keep going. All right, let's talk lava flow layers. I showed you that picture and said, look at that and tell me that lava flows don't have layers. Well, they do. And we're going to start with the basaltic lava flows because those are by far the most common that you'll see along the North Shore. And you've got a bunch of different layers. You've got kind of a ripply, bumpy top. And then all of these dots are air bubble slots that either filled in or didn't fill in with stuff. Some people call it the vesicular zone. Some people call it the amygdaloidal zone. What's the difference? Amygdaloidal means it's filled in with a mineral that's filled in that hole. Vesicular means it's empty. The mineral didn't fill that in. By the way, the minerals that can come in and do that are called zeolites. And we're going to introduce you to the most famous zeolite here in a second. But yeah, there's the vesicular layer. So lots of bubbles there. Down here in the massive zone, the bubbles are a little more organized. There's so many of them, they actually form pipes. And so we've got that going. And then down on the bottom, remember this flow is flowing over something that's already solidified. And so we've got some more pipes down here. We call these pipe amygdaloids. So there's the basics. Now let's take a look at the pictures and see what we got. All right, so here's some layers for you. How's that? And if you look at that kind of stuff, we'll sort this out just in general, but I'm going to show you this picture now and let you start thinking about those different layers and what you're seeing. And let's just take that apart Let's actually show you what the ripply top looks like. It's called pahoehoe. That's how you say it. It's a Hawaiian word because the rocks that are forming in the lava flows in Hawaii are very similar to what we have here in northern Minnesota. In fact, people tell me all the time when I take them out on the rocks at Sugarloaf, wow, this looks just like Hawaii. And I'm like, well, it is pretty much just like Hawaii, except the climate, you know, that's that's a little different. But we do have pahoehoe. These bottom two, or the pictures on the right here are both from Sugarloaf Cove. This one is actually from Craters of the Moon National Monument in Idaho. But you can see where there's been lava flows. Sometimes you can see this ripply top of the lava flows. So that's called pahoehoe. That's when you know you got the top of a flow. One of the things that I do with people on geology hikes all the time at Sugarloaf is say, okay, take a look at these flows and tell me what's the top, what's the middle, and what's the bottom. Well, it's not quite as easy as it seems, and we'll talk a little bit more about that. But legitimately, this is the top of the lava flow.
Hey, Margie.
And then you got, pardon?
Can everybody mute themselves? We're getting some background noise from a few people. Just sorry to interrupt, but if you could just set yourself on mute, that would be great. There's something feeding in. So, thanks. Sorry about that, Margie.
Okay, thanks. Thank you. So here's the next layer down, the bubbly or vesicular or amygdaloidal zone. Some of these are amygdals, the ones that look like dots. Kids ask me all the time if that's seagull poop. I tell them, no, it's not. It's actually crystals. That's our zeolite, are things that can come in and fill in the holes. And then the other ones that are just little round and empties, those are vesicles. So vesicular, and they may have had something in it that's fallen out, or they may not have. So that's the next layer down. And then, oh yes, remember that that whole idea of the most popular zeolite? Well, this is probably it. A zeolite is a mineral that travels through micro cracks in the rock. There's a lot of water in rocks, folks, and most people don't think about that, but it's really true. In fact, if you were to think about all the water in the world, 99% of it's locked up in rocks and we can't get to it. So just put that one in your brain and stow it for future reference. But yeah, the micro cracks allow those water-soluble minerals that we call zeolites to come in and fill in the holes in those air bubbles. Agates, Lake Superior agates, form by layer after layer after layer coming in and filling those holes. And eventually they start out white, and then as the iron that's in there oxidizes, it'll turn red and get that orangey, classic orangey red color that we know of as the Lake Superior agate. So yes, agates are zeolites. And here's a picture of some agates in the rock, still in the basalt. So the massive zone, that's the thick layer of the basalt. And this is probably, well, it is for sure the layer of the lava flow that cools the slowest. I always say that lava flows are a lot like brownies. All right, and if your brownies are hot from the oven, you got that kind of ripply top, sort of crusty, a crusty layer underneath that's got some air bubbles in it. And then you get to that ooey gooey thick part in the middle, towards the bottom. And it does not have the crunchies and it does not have the air bubbles in it. It's just a solid mass. That's the massive zone. But it does have some characteristics that you can look for. This picture on the top just is a looking at that, and you're not seeing a whole lot of air bubbles when you look at that. And I don't know, this is a tough picture to pick it up, but do you see this kind of darker stripe in here? That's one of those pipes that I was talking about. And that's probably one of the most common features to see, but we typically don't see the pipes from the side very often. It's pretty subtle. But I threw a couple more pictures in here. Do you see this rock that's got kind of this round hole on the bottom? And here's another spot over here that's kind of roundish, and another one here. This particular location, I took these pictures because I was like, what is it? I mean, these are these pipes from the top, and I don't know what it is about the mineral content in those air pipes that fill in later with other rock, but the lichens apparently don't liken that spot at all. So I want to, you know, that's one of my mystical, magical, someday I'll figure out why it's that way. But it was a curious enough thing for me to say, I want to take a picture of that. And this one over here is one where that's a little clearer. You've got kind of a reddish color bursting out of this rock. But that's another one of those pipes from the top. But you'll see these round dents in the rock all along the shore. Once you notice them, you'll see them everywhere. So that's a feature that you'll see frequently in the massive zone. Another one that you will see is called columnar jointing. And those of you that have wandered up and down the North Shore could probably tell me exactly where I took these pictures. This one on the right is from Grand Marais, right in the harbor there, on the campground side. And this one is on Highway 61 on the way into Grand Marais before you get to town. Both of these. And what did we have going with this? Well, columnar jointing is a feature of the physics of rocks solidifying. And there's a three-prong thing going on there, a three-prong crack system. And three-pronged cracks line up with each other. It's like mud puddles, okay? We've all seen mud puddles, and as they dry up, you will see very angular shapes. Well, lava does the same thing, except that it doesn't limit it to the very little bit that you see in a mud puddle, just the top. It actually goes all the way down through the lava flow itself, and that's why you see these cracks. Once you recognize these angular cracks for what they are, columnar jointing, you will, there's probably the most common lava flow feature on the North Shore. You'll see tons of them. Here's some examples of other versions of columnar jointing. These two pictures on the left are both from Sugarloaf. You can see these columnar joints close down to the beach. And then you can see this angular in the rock face along the side of the shore on the land side, which is pretty amazing. These are both from out west. This is from Death Valley. This is a lava bomb that flew out of one of the cinder cones out west. This is in southern Washington. And you'll see these features all over the place. Wherever there's been lava flow features, you can see those columnar joints. Devil's Tower is another one. Okay, we've finally gotten to the bottom, the pipe amygdals. So the bottom of the flow, this is the part that's flowing over something that's already solidified. So what's on the bottom is going to solidify quickly too, but there's a lot of gas and a lot of stuff going on. So you'll see these little pipe amygdals. This is probably one of the toughest features to see. These are both from Sugarloaf. And you can see just these pipes that have filled in, again, with a zeolite. They look white. Sometimes they're empty. But if you see them from the side, they look like this. If you see them from the top, they look like woodpeckers have been pecking on the basalt. But it's not. It's actually these pipe amygdals from the top. All righty. So how you doing with basaltic lava flow features? Well, let's go back to this picture, which is also from Sugarloaf. Can you see pipe amygdals? Can you see the massive flow? Can you see the vesicular layer? Can you see Pahoehoe? Well, let me help you out a little bit. Okay, on the North Shore, when you are walking on rock, 9 times out of 10, you are not going to be walking on Pahoehoe. Pahoehoe and vesicular layers of lava flows have a bad tendency to weather away and disappear entirely to allow a massive flow up here to slap down on another massive flow underneath it. But here at Sugarloaf, you can see it. 9 times out of 10, if you're walking on the shore, on the North Shore, you're walking on the massive part of the flow. That thick, heavy piece that doesn't have the air bubbles isn't going to weather. It's got the staying power to stick it out. And so this is massive. Can you see how it sticks out from the stuff underneath it? If you look carefully, and this is hard to see, but that picture that I had on the previous slide of this, there it is right there. That's that same region with the pipe amygdals in the bottom. So this is the massive flow. Here's the pipe amygdals indicating this is the bottom of this flow. And here is the Pahoehoe of the layer below, the vesicular zone. And then you're seeing it starting to boot out again a little bit. Here's the massive zone that's got a bit more staying power. And then here are the pipe amygdals at the bottom. So we've got 1, 2, 3 flows right here that we can identify once we know those layers to look at. So that's stuff that you'll begin to, as you look for it, begin to see more and more. Basically, the bottom line is on the North Shore, anytime you're significantly going up or down, you're probably changing between 2 different flows. And so that's an earmark you can stick in your brain. Now, we mentioned we have rhyolite in places. Here's a couple of well-known rhyolite features. This is Shovel Point as part of Tetegooch State Park, and we all know that this is, oh, my poor brain, my poor pea brain, you all know it. Palisade Head, there it is. Phew, I've been at it too long today. Palisade Head and Shovel Point are both rhyolite, but they're much thicker flows. These guys are anywhere from 80 to 200 feet thick, whereas those lava flows that we have at Sugarloaf tend to be 4 to 6 feet thick. That's an indicator of higher temperature. The thinner the thinner the flow, the faster it was moving. When they get thicker like this, it's slower, it's more explosive, it's got all the bubbles going, all of that kind of stuff. Here's Shovel Point a little bit closer. Took that picture one year on the Winona as it was cruising around on the North Shore. I think I was talking about rocks on that trip for them, as a matter of fact. And okay, remember we said that basalt has a cousin that cools slowly underground. That's called gabbro. A northicite is a type of gabbro. This is right outside the processing plant there in Silver Bay. the taconite plant. And anorthosite is really fairly uncommon on Earth, but it's quite common on the moon. It tends to be the light colored stuff that you see when you see the moon. You got dark spots, and then you're kind of surrounded by white spots. And so anorthosite is the rock that's most similar to what's on the moon. How does it form? Well, these are all versions of gabbro. This is gabbro geeky chart 101. If you're in anorthosite, you're all the way up here on the top. And I always say that it's like the marshmallows in your hot cocoa. It floats to the top, and it's comprised predominantly of feldspar, which is also the lightest stuff, and it'll go right on up there. And it's called plagioclase feldspar, and it'll make huge crystals. This is a spot that you used to be able to walk to there in Silver Bay. They've made the nice park down there. This is actually back behind the plant. You used to be able to walk back there, and all these blotchy things are on there are actually big, huge crystals of pyroxene or plagioclase feldspar back there. Those crystals are as big and twice as wide as your arm. They're just huge. But unfortunately, you can't walk to that part anymore. I keep saying I need to get a contact with the folks at the plant to see if there's access, because it's way cool to see. Like I say, you used to be able to do that, but yeah, things have changed mostly because of bad decisions made by humans who visited that spot. Other well-known anorthosite landmarks, we've got Carlton Peak, that's anorthosite. And also Split Rock Lighthouse was built on anorthosite. One of the things about anorthosite is it's just really tough stuff. 3M came in and had mines. They had a mine at Carlton Peak. They also had one at Split Rock. And I always say, I don't know whether their geologists didn't really have it together or whether they didn't have a geologist with them at all, but they got their start up on the North Shore because they wanted to make sandpaper. And they thought that they had run into a huge series of deposits of corundum, which is a industrial grade ruby, when in reality they'd run into anorthosite, and it made crappy sandpaper. So they did not succeed making sandpaper from anorthosite, but they did eventually find other ways to make sandpaper and develop into the successful company that we know today. But yeah, their start was a little bit rough. And like I say, I don't know whether they left the geologist out of the picture altogether, or if the geologist they had just didn't know the difference between anorthosite and corundum. But there you go. So yeah, that's the rock portion of Lake Superior. And if you think about that continental rift, that's what gave us the basin for Lake Superior. We know that the deepest spot in Lake Superior is almost 1,300 feet deep. And that is thank you very much to that mid-continental rift. But the water didn't come until much later. That came as a result of the glaciers that started. Okay, we said the continental rift was 1.1 billion years ago. Well, the water didn't really come until about 2 million years ago in the form of the Laurentide ice sheets. It got cold. It got really cold. How do you make a glacier? Well, it snows a whole lot more than it melts. That's what happens. And it piles up. And we had, these are continental glaciers that had two serious domes, one to the eastern side of Canada and one to the western side. And here in Minnesota, we had glacial flow from this direction and also from this direction. And I always say, okay, folks, if you want to really geek out on glacial stuff, go to different gravel roads. Go to gravel roads in western Minnesota. They're going to be very different than the gravel roads in eastern Minnesota because the mineral components of the rocks are different. Whole different series of rocks coming from this side than from this side. So interesting stuff. But yeah, glaciers started about 2 million years ago. We had ice cruising all over the place for a couple of million years. Here in Minnesota, we had the older part of the flow. The Illinoisan glaciation went all the way down into Illinois. There are people that will tell you that there are portions of Minnesota that are driftless zones that didn't get glaciated, and that's really not true. They actually did get glaciated. It's just that the end moraines, the Wisconsin era on the other end of the 2 million years, was the most recent part of the flow. It missed southeastern Minnesota, but the earlier stuff did not. This is the driftless zone, and it's all in Wisconsin and this itty bitty teeny weeny little bit of Illinois. So there you go. Looking at how the glaciers flowed into the state. And you got to think about glaciers as gigundo bulldozers, just kind of pushing everything along with them as they go. The glacier conveyor, they call it, where it scrapes stuff up and slides it around and pops off in places. The very end of a glacier will have what's called a terminal moraine or a dump zone for all the things that have been picked up from the glacier. That's the front of the bulldozer just pushing it all through. As the glacier retreats, there's a recessional end. You can have drumlin fields. Drumlin fields form when the rock is a little tougher on one end and the ice kind of has to go around. So you get these drumlins. Google Earth, northeastern Minnesota, and you can find drumlin fields by looking from the top. Eskers are under ice river areas. Cames are spots where there were little places that filled with ice and later became little lakes. We've got all of that kind of good stuff going on. So those are some of the glacial landforms. And here, this is what I like doing. I like taking a look at the glacial advances. You can look at the geologic map of Minnesota and see that reflects it. But where it really tells the tale is looking at the topography. Can you see where the glaciers came? Oh, you sure can. You can see this whole Minnesota River Valley and the Red River Valley on this side. You can see the St. Louis lobe coming on in here. You can see the residual of this one coming on through the Superior lobe. All of that kind of stuff relates to our current geography, thanks to all of the glacial stuff. And as the ice started to retreat about 12,000 years ago, so from 2 million to 12,000 years ago, we were covered with ice. And as that retreated, we've got moraines that are on the end. As the ice retreated, it began to melt a little bit. It formed a really high lake that we called Glacial Lake Duluth. And as that retreated, by the way, all right, all of the folks that come from the metro north, you get to that spot at the top of the hill, Thompson Hill, where the rest stop is, and the whole lake and the whole industrial valley of Lake Superior opens up and you're like, oh, I'm at Duluth. Well, that's former beachfront property. At this point in time, That's where you are. You're up there. And then as the ice retreated, we didn't get as much water. Oh, and by the way, this is an interesting thing. Initially, the water traveled south on what was the Mississippi water flow. But as the ice retreated, the direction changed and shifted to the east and what's now the St. Lawrence Seaway. And that's because of something called glacial rebound. Imagine ice, okay? We've got enough of it piled up right now, and we've all got spring fever consequently. But this is nothing in comparison to those glaciers, which were 1 to 2 miles thick. All right, so every gallon of water weighs about 8 pounds. Hello, that's a lot of weight. But as that ice retreated, the land started to bounce back up. And in fact, it's still rebounding today at about 10 centimeters every 100 years. So it's still coming back from that massive ice flow, but it caused the shift of the water flow to go east until we finally settled into our current state of affairs with Lake Superior at about 600 feet above sea level. Here's a map of different levels. Okay, we've got the whole basin is filled. That mid-continental rift basin is filled with ice, but as the ice retreated, we had various beaches along the way. Right along the shore, you can pick this one up, which is just above our present lake level. At Sugarloaf, you can see that very easily. It's about 60 feet above the other one. So some interesting stuff going on. Thank you, glaciers. All right, well, I've been blathering for a long time, but I did want to leave you with a few things to look for as you're cruising up and down the North Shore, getting ready for summer now and being able to see rocks again. Along Highway 61, there are some really interesting spots. A lot of you probably can recognize this as, again, right before Grand Marais, this is Cut Face Creek. What the heck? We got this dark black rock up here, and then we've got this red stuff down here in layers. Well, it turns out this red stuff down here is sandstone. Okay, wait a minute. Sandstone is a sedimentary rock. What the heck? We've said this is all about igneous rock that came from molten lava inside the earth. How did this happen? Well, here's the deal. And this is something the geologists have been puzzling about for a while. We know we've got hundreds of flows up and down the North Shore, but we don't necessarily know much about the amount of time that lapsed between flows. Remember I said that we had lava flows for 15 to 17 million years. Well, it might have been 7,000 years between flows, or 70,000 years between flows, or 7 million years between flows. We don't know, and that's stuff that we're still trying to get the answers to. But when you have rock weathering, which is what happens to make sandstone, it weathers down, and this is rock that is normal here that has weathered down to its sandstone and reformed as sandstone. And you can see all these layers in here. This probably at one point in time was standing water, like a lake system there temporarily, and it piled up a whole bunch of stuff in those layers. If you go further up around the corner from that, you'll find lots of thompsonite, another one of those special zeolites. But you can find big chunks of thompsonite in the roadside cut there if you know where to look. Kind of interesting stuff. All right, so that's a fun place to check out. By the way, we know that this probably was moving water because there are ripples reflected in the sandstone. If you walk across from the rest stop that they put in down below at Cut Face Creek, and you walk on the other side of the highway and start exploring up in that valley up in there, you will find those ripples in the rock recorded there to tell you that that probably was standing water at one time. Way cool adventures to have with rocks. Here's another sandstone. This one is between Lutsen and Tofty, but this one looks different. We can see the layers in here. This is what they call the deer yard sandstone, and this is cross-bedding. There's rock that goes, a layer that goes this way, and then there's layers that go this way. Cross-bedding happens either when you have a lot of wind or if you have a lot of water movement like a creek or a river. So that was more likely what was going on here. But you can see this alongside Highway 61 if you're looking carefully as you're cruising along Highway 61. Here's some cross-bedding. This is right behind the Rose Garden in Duluth. So there's another place where you can find cross-bedding. Here's an oddball. Anybody know where we are here? If you're guessing close to the Canadian border, you would be right. This is older rock. This is slate that is right up close to Canada. And this is in that 2.5, 2.7 billion year old stuff. There's just a little segment of it sticking out there right along Highway 61 just before the Canadian border. So that's a fun spot. This is down in Duluth. I always say these are like donut holes. This is contact metamorphism, where molten lava is coming in and filling in around some boulders. And the edges of those boulders are changed a little bit from the heat. So that's something that you'll see frequently. This is along the Lake Walk in Duluth. Oh, and here's another geology joke for you. Anybody know where we are? Which river coming down the shore? Well, this is the Temperance River. And the Temperance River is kind of unique because it's solid rock face all the way to the shore. Consequently, there isn't the usual weathering that you see at the mouth of a river, the deltas that you see from the gravel and the rock and so forth deposited. Temperance got its name because this river has no bar. There you go. Bad geology joke, but it's the truth. It's actually a geology joke, is how Temperance River was named. This is right on the other side of the Silver Cliff Tunnel. Some fun stuff going on here. Lots of zeolite stuff in here that gets all crusty and crinkly in there. But we've got diabase, which is the kind of basalt or gabbro is a gradation, and this is getting a little more crystal in it to make it a little more crystally. And then, yep, we've got an andesite on the other side, and that's another gradation between rhyolite and basalt. So all kinds of interesting stuff. And this spot, this is a terrible picture, but here's a spot about mile marker 62 along the shore. And this one's curious because if we're looking at it closely, we will see pipamygdules here. And then we will see pohoihoi here, vesicular zone, massive, and more pipamygdules up here. But the problem is, it's upside down. Whoa, something happened there. Probably some pretty hefty movement going along there that happened and actually flipped a lava flow upside down. Very curious, very interesting little mystery. This is Kennedy Creek. This is anorthosite. Not all anorthosite is nice and white. This is nice and black. And finally, this is the new cut that they put in to put in that rest stop down just south of Split Rock. And I love this, and someday I'll get smart enough to be able to post all of these pictures together, but it's kind of interesting. As you're driving along on this, can you see the columnar jointing? That angular, very sharp faces, and it tilts. And this is the southern end, or towards Duluth side. And we're gonna move, I'm gonna take a series of pictures here. We're gonna move a little bit closer to Grand Marais as we cruise along, and look what happens. And you can easily walk this, park in the rest stop and then use care, but you can walk this. Oh, they're coming. They're not quite as steeply tilting to the south. Oh, they're straightening up some more. Whoa, look at what happened here. The whole thing bent like spaghetti. We don't think about rocks being that flexible, but they can be, and they can bend. And then as we continue back the other side, they're staying a little straighter up. But yeah, all kinds of interesting things to explore in the world of rocks along the North Shore. Hope we have given you a few things to look for the next time you cruise up the shore. Thanks for coming, everybody, and I'm happy to stop the share here and give you a chance to throw some questions at me. Bloop. There we go.
What's in the vesicles?
What's in the vesicles?
Yes.
They are water-soluble minerals. Sometimes if it's quartz, it'll make an agate. If it's Thompsonite, it'll make Thompsonite. Some of the other common ones that we'll see, there's a white one that's usually calcite. There's a green one that's called epidote. There's a pink one that's called lamantite. So you can see all kinds of colors in those holes as they fill in and make those amygdals. Just depends on which mineral happens to be cruising into the rock there.
Are any of them empty though, or just filled with water or air?
Yep. Some of them never filled, and so some of them are empty. And those are called just straight vesicles. So if they fill in with stuff, they become amygdals. If they stay empty, they stay vesicles.
I was reading an article about basalt absorbing CO2 and they were talking about it could go into the vesicles.
Say that one again.
I read some article that basalt reacts with CO2 and
Okay.
CO2 and that it can go into the vesicles.
I have to say, I don't know anything about that. I'll have to do a little bit of snooping and see what I can figure out. Anybody else on the geologic circuit that's in this group? Anybody speak to that one? Okay, sorry, I can't talk about that one because I'm not familiar with that, but I'll have to do a little more snooping. Like I say, I'm not a geologist by training. I'm just by love of the subject and learning more.
Someone said something that's a very slow process. Carolyn said it's a very slow process. That
okay, well, it makes sense that some of those water-soluble minerals are carbonates, so CO2 could be a component in that. But yeah, interesting. I'll have to check that out.
Could you repeat that question? Could you repeat that question, please?
Yeah, she was asking if CO2 played a role in some of those crystal formations inside the air gas bubble vesicles that fill in over time and become amygdals. And I said, boy, I haven't heard anything about that, but it seems reasonable because many of those things are carbonates or carbonate links. So it doesn't seem like a far-fetched theory to me, but I would want to do a little more snooping on that before I gave you any definitive answer.
I think that part of the idea is that there are quite a few research papers that show that currently you can force basalt to absorb CO2. So it's part of that geomineralizing idea.
Sounds good to me. More good news. I always knew rocks were special. This is more on the side of special for rocks. But I'm
And
going to have to do snooping.
Carolyn just put a link to an article in the chat.
Oh,
so if you know how to
awesome.
use the chat, if you're go to the bottom of your screen, it'll bring up a bunch of icons, and there's the chat. And she put a link in there that everybody can see. Yep.
Yeah, I'm going to have to see if I can copy that and stick it somewhere so I can play with that at some point later on.
I'll save the chat for us too.
Oh, good. Okay.
I'll try to remember.
All right. Everybody else still awake? Anybody else? Other questions?
I'll have to come up to Sugarloaf and do a live walk with you on the beach this summer.
Yeah, I usually do those on Sunday mornings during the summertime. We'll see what happens with that. But that's, I mean, that's a solid tradition that I don't see any reason to change necessarily.
Go ahead, Dan.
Oh, hi, this is Dan Billman. Can you hear me?
Uh-huh.
Great. At one point, I think I heard you say, because the ice from the glacier is basically melted and gone away, now the crust is moving upward vertically, and I think it was something like 10 centimeters in 100 years.
Uh-huh.
So that'd be about 4 inches in 100 years. But I'm thinking about that with the water in Lake Superior having once been hundreds of feet higher than it is now, has the amount of water generally decreased a lot to explain that change?
Well, I'm sure it's changed some. I mean, obviously, the original volume of Lake Superior, or Glacial Lake Duluth, if we want to call it at that stage of the game, had much, much more. I mean, we have 3.6 quadrillion gallons roughly in the lake in its current state. So yeah, we would have had significantly more when the water was higher. And as we tend to as global warming changes the lake levels, we've been predicting, the prediction has been that global warming is going to cause the lakes, the lake level to drop over time. And certainly the glacial rebound can be a minor player in that as well. By the way, the glacial rebound is much greater on the North Shore side than it is on the South Shore side. And that's linked to the geology as well. So yeah, we'll have the tilt going this way towards the South Shore. So yeah, but we've got a deep trench on the North Shore already. So yeah, I don't know that we'll be hurting terribly, but but it will change, and I'm sure that that's going to be part of the story. Always more things than you think about.
Well, thanks. That's interesting. And thank you for your whole talk.
Thank you.
Yeah. Yeah.
Uh-oh.
The Minnesota Geologic Survey, you can download a whole bunch of those maps electronically.
Oh, cool.
So go on the Minnesota Geologic Survey and start digging around for all of things that you can download. It'll keep you busy printing for years.
Okay,
thanks.
Did you mention Dick Ojekangis's book on Minnesota geology? Because that's just chock full of really good stuff.
Yeah, that's a great book. That's a phenomenal book. And the other one that I really like that you might be able to get at the state parks is John Green's book about the geology of the on display
Oh,
about the state parks. This
yeah,
is
that's a good one,
phenomenal.
too.
It's out of print, but they still have some of them in.
Recent book on the Great Lakes in general that's pretty interesting, called Great Lakes Rocks.
Cool. Who's
Very
the
good.
author?
And if you like glaciology, there's an older book written by Dr. Charlie Match out of Duluth, who's
Yep.
no longer with us, called the North American Ice Age. It's also out of print, but it's very, very good.
Yeah,
Charlie Match and John Green were my professors when I was at UMD. That's how old I am.
And they both led very good expeditions when we were up the North Shore.
yeah, I know both of them. Actually, all three of them: John Green, and Charlie Match, and Dick Ojekangas.
Uh,
I've interacted with all of them, and Jim Miller. There's some wonderful stuff. Jim Miller's the next generation, who's also retired. So, yike. Yep, exactly. Yeah, I have a fantasy that someday I will travel all over looking for the normal glacial till kinds of things that we see on the North Shore, and I will make a map as which rocks came from where. Someday I'm going to do that.
wow.
But yeah, I'm going to have a whole lot more travel time and a whole lot more bebopping around. But yeah, that's one of my crazy fantasies. All right, well, everybody's slowing down. Thanks so much, folks, for coming out. And again, if you enjoyed the presentation, feel free to help us out with continuing to be able to do these kinds of things by dropping a little donation in on our website. Great stuff.
And this presentation has been recorded. Hope to get it up on our website next week to our YouTube channel. So just watch on the website and we'll have it up for you.
Thank you, Molly. Great.
All righty.
Thank you.
Thank you, Margie.
Thanks, everybody. Take care.
Good evening.
Come visit.
Margie, I saved the chat somewhere in my computer.
All right, good deal.
I lost internet a couple times just for the last 5 minutes, so hopefully everything's all right. It should have kept recording, but all at once
gee.
this is the problem. We just go off on. Then just the other weird thing is your computer had some weird feedback going. So you'll see those conversations in the chat. It's that computer. It's got to be that computer's microphone. So
Yeah, I think it's a little bit funky, and I've noticed that with some of the meetings that I've had too. It hasn't been horrible, but yeah.
everybody kept saying, tell everybody to mute their mics. I'm like, it's
They are
not
all
them,
muted.
it's Margie. So
All right.
you'll see those conversations, and there's a lot of thank yous and great jobs in here, so in the chat. So
Yeah, well, there's a lesson to us that we need to not do presentations for Zoom off this machine.
yep, that's what I told somebody. And let's see, I think John Dolmar may help out a bit with that. So
Oh, that's wonderful.
he wants me to email him. So yeah. Hi, Mom and Dad.
Good
I
deal.
can see they were on.
Wow, lots of stuff here.
Yeah, can you see the chat? I'll
Yeah.
save it again, just so, because I never know where it goes. Show in folder.
Yeah, it's always fun. I
Yeah.
forgot to tell people to say where they were.
And when I got booted back on, for some odd reason, it was showing me the poll.
Oh, that's bizarre.
But it didn't show it otherwise, so.
Let's see. Oh, you're logged in from another device. My polling session is inactive, so you've got it now.
Yeah, it bopped over to me. Isn't that weird?
That's funny. Well, it probably is there when you first log in and something is wacko with that. I don't know, but.
So I'll be able to look at the poll. Oh yeah, we had 45% email from Sugarloaf. We had 3 people who did the interview, WTIP interview, website 5, and then other 56. And we had up to 125 people, so at one point, including you and I. So
Yeah, I figured you
Right.
were, I could depend on you to log that part.
yeah, that was amazing. So I'll have to convert this when I get to my parents' house and, and use that internet. So
Yeah. Yeah.
okay,
All
can end polling now.
righty. Well,
Thank
yeah,
you.
Yeah, you're welcome.
Molly,
Thanks, everybody.
Yeah, somebody's
Tank fell asleep.
Oh, Tank fell asleep. The cat.
Oh, it's like, who's Tank? I put somebody to sleep then.
Tank's always asleep. Don't worry.
Okay.
It must be
Okay.
why all of these other people are still here. I put them to sleep and they don't know that it's over.
Oh, Dana's there.
Okay, let's see.
See you tomorrow. Okay.
Yep, good night.
Bye-bye, everybody. I'll end.
Bye-bye.